Hey, let's take a look at 6.2, Properties of Parallelograms. This whole chapter is on quadrilaterals, but a big part of it is about parallelograms, because parallelograms are a special type of quadrilateral. In a parallelogram, you have all kinds of relationships, and if you look at this picture, you can see I have a quadrilateral, and I've shown in the picture the parallel sides. Opposite sides will be parallel. Okay, now that's going to start introducing some other properties. And so if you look at this, there's a lot of different things. And in class, we talked about some of the different things. For now, we're just going to list out, hey, what else would you know about this parallelogram? So here we go. Let's start listing them out. Some properties of parallelograms. Number one is the definition of a parallelogram, which states that opposite sides are going to be parallel. So both sets of opposite sides are parallel. Now, because you now know that the opposite sides are parallel, all kinds of different other relationships can pop up. One of them would be that opposite sides also end up being congruent. And opposite angles are congruent. You can see in that previous picture that I put the diagonals in there for you. Okay, now sometimes the diagonals are important and sometimes they're not, depending on what type of quadrilateral you're dealing with. In this case, they're not the same length. Sometimes we think things are always going to be congruent, but they're not. If you look back at that picture, there's one of them that's stretched longer than the other one. But the diagonals do have a feature where they bisect each other. So where they cross is the midpoint on each other. Okay, that's a good one. And then I have one more feature that we're going to talk about, and that is the consecutive angles. Now, if you look at consecutive angles, you'll always notice that one is going to be obtuse and one is acute. Okay, so they're not going to be congruent, but consecutive angles, and it has to do with the whole parallel lines cut by a transversal thing, that consecutive angles in a parallelogram, and by consecutive I mean one right after the other, as you wrap around. Maybe I should show that in a picture here. The consecutive angles, and I'm ignoring diagonals right now. Ignore those diagonals in there. This angle right here is consecutive with this angle here. As you wrap around, you could say that this angle right here is consecutive to this angle. And as you wrap around, consecutive means one right after the other as you wrap around. Okay. And again, not congruent because one's acute and one's obtuse. But what they are, if you look at the whole parallel lines cut by a transversal, these are same side interior. Okay, same side interior angles are supplementary. So we say that the consecutive angles in a parallelogram are supplementary. So we have all these different properties that we can use to find out extra information. So that's what we're going to focus on today, getting familiar with these properties. In this picture, I've labeled several things, and we're going to use, so kind of keep that list handy of all the different features that we know. We know that we have a parallelogram. This is our notation for a parallelogram, and it even has in the picture marked opposite sides are parallel, so we know that. It asks us for the measure of angle A. Angle A is down here. Now I have a couple things with angles. I say opposite angles are congruent, but I don't know angle C, so that's not going to help. But that last one we said consecutive angles are supplementary. So if this one is 127, then I can subtract that from 180 to find out what angle A is. So where am I going to, I'm going to squeeze this in just off to the left of number one there, where it says measure of angle A would be 53 degrees. Okay, let's try number two, the measure of angle D. Okay, now there I do have opposite angles. Right here, opposite angles are congruent. I could also, since I now know A, I could do consecutive angles are supplementary, but this seems pretty straightforward. Opposite angles are congruent. So the measure of angle D would be 127 degrees. All right, now let's look at number 3, we're dealing with x here. And you can see that x is tied up in these side lengths. So this side is x plus 2, this side is 2x minus 3. These sides are parallel, but more importantly, our property from the previous slide there is that the opposite sides are congruent. So I'm going to set up an equation here to find x. I'm going to say x plus 2 needs to be equal to 2x minus 3. And then if we go solve for x, I find out that x is equal to 5. So then I got that answer there. And then the last one is find the length of AB. Now that I know what x equals, I can just plug that in. AB is x plus 2, which means 5 plus 2. AB is going to be 7 units long. Okay, so not too bad to stuff there. Some basic just congruent supplementary kind of angle stuff, and then a little bit of algebra problems. All right, let's try a little bit more. It says find the values of x and y in the parallelogram at the right. All right, so when I look at this one, I have the diagonals drawn in. So when I'm looking through my list of properties, I'm going to be using the whole diagonals are congruent. I'm sorry, diagonals are not congruent. Diagonals bisect each other. So remember I said that this is kind of the midpoint for this segment, but it's also the midpoint for this segment. Now, I was hoping this was going to be easier, but this is going to take us a little flashback to Algebra 1 because this segment here will end up being the same length as this segment because that's the midpoint. So I would set 3y minus 7 equal to 2x. That's going to create two variables. So that's a little bit more of a challenge. Over here, I could go this way. X plus 1 is equal to y. Again, two different variables. But if you'll remember from Algebra 1, we call that a system of equations when you have two equations that have two variables. So I'm going to start off, and I'm going to kind of write this in an order that maybe will help you set it up. I'm going to start with this segment here, y is equal to x plus 1. That's one of my equations. The other equation would be that 2x has to be equal to 3y minus 7. Now we have you actually had 3 ways to solve a system of equations in Algebra 1. This was the thing where you could graph them and you look at where the two lines intersect, or you could do substitution, or you could do elimination where you line them up and try to get one of the variables to drop. All 3 of those are great methods to solve the system of equations, but this one is set up beautifully for substitution because you already have this y isolated. I know that y is equal to x plus 1. So what we do is we grab this x plus 1 and we substitute it for y over here. So let's look at what's going to happen when you do that. I'm going to take this x plus 1 right here and I'm going to plug it in for y because that's what y equals. And my equation turns into 2x equals 3, and then in parentheses I'm not going to put the y, I'm going to put the x plus 1 minus 7. Does this ring a bell for you? Do you remember doing this? 2x equals, now distribute. If you'll notice here, what I've managed to do is I got rid of the y in my equation, and now I just have this equation with x's in it. And that is something that I can solve. This is going to be a negative 1x equals 3 minus 7. That's negative 4. Divide by the negative 1. X is a positive 4. So now it says to solve for x and y. I've got the x. Great. Now what I do with that x is I go plug it back in to one of these original equations. It seems like it'd be pretty easy to plug it in right there. Y is equal to x plus 1. So that means y is equal to 4 plus 1. So y is going to end up equaling 5. That's not too bad. It was set up pretty nice for substitution and a good flashback every once in a while to see some of that algebra stuff because it's going to come back to you in Algebra 2. All right, and here's a flashback for geometry for us, is where it's asking us to do a proof, and we haven't done proofs in a little while. So always nice to throw one in there once in a while and keep it fresh. So here we go. Let's set up a nice 2-column proof. These are going to be our statements. These are going to be our reasons. We always start with the given. This is a parallelogram, A, B, C, D. What that tells us is all those properties from that original slide, I know all that information just by them telling me that it's a parallelogram. All right, the other thing I know is AK is congruent to MK. That's all given. And let's maybe mark up the picture a little bit. At least with that congruence, it says AK, this right here, is congruent to MK right here. All right, so if you ignore all the little lines inside of this and just look at the big triangle, AKM, if those two sides are equal, then this is an isosceles triangle. This leg's the same as this leg. It's an isosceles triangle. And what do we know about an isosceles triangle? Well, we know that the sides are congruent, but remember that if the sides are congruent, so are their base angles. These two angles would be congruent to one another. That's called the isosceles triangle theorem, so I have that information out there. But I got ahead of myself. What are we even trying to prove here? We're trying to show BCD. I'm going to mark that so I don't lose track. There's a lot of angles in here. Angle BCD, this angle right here. Just going to put a dot there because it's not, I don't really know anything about it yet, but I know I want that angle to be in the same as angle CMD. That's this one right here. Okay, that's kind of weird because these are not really angles within this little triangle. This is not really part of the big triangle, but somehow I got to get these two to be congruent. Well, I like that that we're dealing with this because remember what I just said? This side's the same as this side, so then the base angles are the same. Okay, and I know ABCD, this thing right here, this is a parallelogram. So it has all those properties. Okay, I think I could get A involved in this, right? Base angles of my isosceles triangle are congruent. All right, and then look at these two angles. What are those things? Those are opposite angles in this parallelogram. I'm kind of dealing with the same angles over and over. Let's set this up. All right, I'm going to go ahead and go into step 2, and I'm going to say that angle A is congruent to angle M. And that's called the isosceles triangle theorem. Remember, if the sides are congruent, then the angles are congruent. Isosceles triangle theorem is what that's called. All right, I'm going to go ahead and mark that in my picture. I know that this angle is the same as this angle. Now if I kind of used up my given piece on the congruence. Now let's look at the parallelogram they told me. If I look at the parallelogram, and again I'm just dealing with angles here, so if we were to look at just this parallelogram and I just talked about angle A and I want to be talking about angle C eventually, these are opposite angles. And since that's a parallelogram, then I'd say the opposite angles are going to be congruent. I'm going to go ahead and put that in there then. That angle A would be congruent to angle C. The reason that we write is just all those different properties that I listed, those are all theorems, really, is what those are. So I just list out what that theorem said, and it said opposite angles in parallelogram congruent. Just kind of shortcutting that property that I have listed. All right, and so that's a theorem. And look at what you have here. A is the same as M. A is the same as C. So wouldn't M and C have to be the same? Okay, I think so. Now, I wrote it like this so you could see it a little bit easier, but here's the thing. I got to sneak back here. I can't really call that angle C because I have gobs of angles sitting right there at angle C. There's all kinds of things. So angle C is kind of vague. I'm going to call it angle BCD, which is part of my proof anyway. And now, I did call this just angle M, and that's okay. They happen to call it CMD, but there's only one angle there, so either way works. All right, and if they're both congruent to A, then they're congruent to each other, so I'm going to say angle BCD is going to end up being congruent to angle M. I'll go ahead and match their angle M, angle CMD, and that's just a transitive property. If they're both equal to A, then they're equal to each other. All right, how's that a flashback? We kind of hit several things. Got some new stuff, some old stuff. Good little proof there. All right, now the last thing that I have is this last theorem that's not really specifically a parallelogram, but it deals a lot with parallel lines. So the theorem here says that if 3 or more parallel lines are cut off into congruent segments on one transversal, then they're going to cut off congruent segments on every transversal. So let's explain what that means. You got parallel lines, and it says 3 or more. You could have more if you wanted, but you got these 3 parallel lines, and you cut it off with this transversal, let's say. Now, they're specifically cutting that through there so that this segment here is congruent to this segment here. Well, what that means is that any transversal at all that you throw through there, for instance, this one here, it's going to cut it off into congruent segments too. So you can see that this little piece ends up being the same as this little piece. And if it works on one transversal, it's going to work on any transversal. All right, so if you come down here I have 4 parallel lines. And it tells me, here, let's start filling in what we know. EF and FG and GH all equal 6. This is 6. This is 6, and this is 6. Okay, so it cut it off into equal or congruent little segments. Okay, if AD is 15, what would CD equal? Well, if the